Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II. So today we will continue our study of nets, module 29, cofinal families, subnets, etc. So let us begin with a definition. A subset D prime of a directed set T is said to be cofinal if for each A inside D you must have a B inside D prime such that this B follows A. If you have a net D to X, that will be called frequently inside a subset A of X if S inverse of A is cofinal subset of D. Okay, so this is the same thing as saying that given S inverse of A must be cofinal subset. So all this B, so whatever B you get, B should be inside this S of B must be inside A, right? So this, you take this as D prime, given A inside D, I must get a B inside D prime such that S of B is bigger than B follows A and S of B must be inside A. That is the meaning of this. S inverse of A is cofinal. Okay. S inverse of A is cofinal, same thing as now S is frequently inside A. Okay, which is somewhat weaker than eventually inside A. Okay, eventually a constant function is much more stronger than having just a subsequence being there, right? So this is somewhat like, we may say there will be a subsequence, but we will see that there is a notion of subsequence, there is a different notion here. Okay, for subnets. So it is easily seen that eventual subset is cofinal, but converse is not true. Okay, that I have indicated. Even you can have examples of sequences themselves wherein this is not true. So another remark is a cofinal subset of this Nx. Remember, Nx is a directed set in any topological space, is nothing but a local base. Remember that definition. Given any open neighborhood of X, that is given a member of this one, there exists a member here which follows that. This is the same thing. There exists a member in the local base which is contained inside the given member here. So that was the definition of local base, right? So every local base is nothing but a cofinal subset of this Nx. Therefore, they will do the job of this Nx quite often. The following lemma is obvious. So that is precisely what I mean for saying that the cofinal families take care of the convergence properties of the original thing. Every cofinal subset F of a directed set is again a directed set with the same direction restricted to the subset. Moreover, if S from D to X converges to X inside X, then so does S restricted to F. Okay, so that is why they do the job, is what I said. But they may not do everything that is the original thing can do. If you took all of them, then they will do the job. That's the whole idea. A subsequence of a sequence, okay, of sequences is a cofinal family of as treated as a net. A subsequence can be thought of as a net, where sequence itself is thought of as a net. That's all. So both of them, you take the net, then a subsequence will be a cofinal family in this sense. Okay, cofinal word is used even within sequences also anyway. Okay, one more definition. Now we are coming closer and closer to the convergence property. Take any net in a topological space. A point is called a cluster point of S. Earlier we defined limit point, okay, limit of a set. Now cluster point of S, if and only if S is frequently in every neighborhood of X, which is same thing as saying that S inverse of U is a cofinal subset of D for every U where U is a neighborhood of X, which is the same thing as say, given A inside D, there must be a B inside D such that A is less than or equal to B and SB is inside U. Okay, so this is the notion of cluster point. Just like subsequence converging, so cofinal thing converging, we will call it as cluster point. All right. Now here is the lemma which relates the property of being cluster point. Take any net. Suppose there exists a cofinal subset f of D such that S restricted to f as a net converges to X. Then X is a cluster point. Okay, one such cofinal family is enough. S restricted to f converges to X implies, given a neighborhood U of X, there exists X belonging to F such that F belonging to B, A is less than or equal to B implies B inside U. Okay, so this is the meaning of S restricted to F converges to X. Okay, to show that X is a cluster point of S now, given any P inside D, choose Q such that P less than or equal to Q, okay, and A is less than or equal to Q. You have an A and a P, right? P is there. So take one which is bigger than both of them, which follows both of them. That shows that S is frequently inside us. Okay, hence we are done. See, as soon as A is less than or equal to Q, S of Q will be inside you. Right? So, what is the conclusion here? The cluster point is generally a generalization of a cluster point of a sequence in analysis. There we have a strong theorem, namely a point is a cluster point of a sequence if and only if there exists a subsequence which converges to it. This leads us to think about a notion of a subnet of a net, like a subsequence. Okay, first of all, let us recall the correct definition of a subsequence. Okay, sometimes some books don't give you, so I am going to give you that one. T from n to x, okay, of a sequence S from n to x. Namely, we must have an order preserving function P from n to n such that this T is S composite P. Okay, it is like a reparameterization, right? So order preserving map one way. Okay, then this T is a subsequence of S. Experience tells us that a simple-minded generalization like this, replacing n by any two directed sets, would not be enough. Okay. See, all sequences are the domain of same n, but when you take all nets, the domains keep changing here, right? So if you just say there is an order preserving map from one to the other, even that may not be enough. So you have to be cautious here. So with sufficient experience, we have come across this definition. There is a scope for improving or making it more complicated, or whatever I would like to say. All these things are not hard and fast rules, right? So you are free to think of doing something different also. So here is a final, I say final definition as far as the existing theory is concerned. Start with a directed set and a net inside X. By a subnet of S, we mean another net from another, right, another directed set E comma this prime, such that there exists a set theoretic function P from E to D, just a function, set theoretic function from E to D, such that our T is nothing but S composite P. This is the first thing. Now, in the definition of a subsequence, we have order preserving relation here, order preserving map here. So that is replaced by a weaker condition here, S2. Okay, this S is for subnet, S2. S2 says the following: for every D inside D, you must have an E inside E, such that for all E prime which follows E prime, E less than or equal to E prime, D must be followed by P E prime. So P E prime should come after D. Okay, so that means the property of P. And we take such a P, take T equal to S composite P, all such T will be called subnets of S. Okay. So this is reflecting cofinality here. Okay. Of course, we have to bring P here. If P were an inclusion map, then it would have been just like a cofinal map. If E prime is a sub of D prime, then it would have been the same thing. But we want to prove any two sets. So they are related by a function P which has this property. So this becomes a far superior definition indeed. Let us see whether it works or not. If you make too weak a definition, then it may not be good enough. That's right. The first condition says, okay, as in the case of subsequence, okay, this is the definition of like a subsequence. Okay. But we have given up on the order preserving requirement of P. Instead of that, the second condition is something like, if E prime goes to infinity, P prime goes to infinity. This is like that, you see. So E primes are larger than E, then P primes are larger than D. Okay, that is like epsilon delta definition of function going to infinity if you do correctly. So it is similar to that. Okay. So analysis is the guide for all these things after all. What happens there, the experience there, that's all. Notice that every subsequence of sequences is a subnet, if S is thought of as a net. Also, we can easily get examples of subnets of a sequence which are not subsequences. Okay, very easy to get. Just obliterate one element so that it's not order preserving. It has no effect on the rest of them. It will be a subnet, but it will not be a subsequence. That's all. Thus, This definition of subnet is a liberal generalization of a subsequence. Okay. So one more remark here. One is tempted to compare the two concepts, a cofinal family and a subnet. Indeed, if F is a cofinal family in D comma whatever partial order direction, then with the restricted order it is a directed set, right? Also, given any net S from D to X, taking P as the inclusion map, it follows that S restricted to F is S composite F is a subnet. So that's what I have told you, that cofinal families do give you subnets. Thus, okay, we see that the concept of a subnet generalized is the concept of restricting a net to a cofinal family as well. Okay, so we can now strengthen the earlier lemma that we had proved, namely now it is if and only if. Okay, in terms of cluster points, take any net in a topological space, then X belongs to X is a cluster point of this net if and only if there exists a subnet T converging to X. Okay, we had seen that there is a one part, if there is a whatever cofinal family restricted, that it converges. Now, in terms of subnets, you have got if and only if. Let us look at if part. That means what? If you have a subnet converging, then X must be a cluster point of S. Okay. So let T equal to S composite P from E to X. That is, suppose this is subnet of S, and let us assume that it converges to X. Take a neighborhood U of X. There will exist some E1 inside E such that E1 is less than or equal to prime. This is a relation inside E, right? E1 less than or equal to E prime implies T E prime is inside U. This is the convergence of T. Now, given a D inside D, I am going to now the original directed set. First, choose E inside E such that E prime less than or equal to E less than or equal to E prime implies D is less than or equal to PE. This is the property of P. Okay, nothing more than that. I am repeating that property here. Now, take another element E2 inside E such that this E2 is following both E1 and E. Okay, that is possible because E is a directed set. So E1 is less than or equal to E2 and E is also less than or equal to E2. It follows that D is less than or equal to PE2 because what? E2 is bigger than E, so D is less than or equal to PE2, and S composite P of E2, which is T of E2, that will be inside. Okay, because as soon as something is something is bigger than E2, T of that is inside U2 is the first part here. Therefore, S is frequently inside U. Okay. Hence, X is a cluster point of S. Okay. So one way is done. Now the only if part. The only if part you have to work little harder. Suppose X is a cluster point of S. I have to construct a subnet which converges to X. Okay. Such a thing is not possible in an arbitrary topological space with sequences. Okay, there may not be enough sequences at all, right? So this is something which the nets have an advantage over sequences. So let us see how it's done. We take ordered pairs D comma U belonging to D cross Nx. Okay, with the property that S of the first coordinate, S of D, is contained inside you. S of D belongs to you. Okay. All right. What are U? U raise over neighborhoods of X. Okay. So obviously, every element of an X is non-empty. Okay. So this S has this property that SD is inside U. So that is my definition of the set E. Now what is the relation? Relation is again a strict relation coming from D cross Nx. Nx has a relation, D has a relation. Take the strict relation, namely du less than or equal to prime D prime U prime if and only if D is less than or equal to D prime. That is the order of D, direction in D, and the direction in Nx is by reverse inclusion. U contains U prime. Okay. We need to check that this is a direction on E. Okay. This is not true in general. We have to use somehow the property of S, namely X is a cluster point of S. Only because of that this is working. Okay. In any case, transitivity, reflexivity are obvious. Okay, there is no problem. It doesn't depend upon SD. They are true inside D cross Nx, so they will be true here also. The problem is about the third point, namely direction. Next, let D1 U1, D2 U2 belong to A. We must find out a D3 U3, right? Such that which is bigger than or follows both the two elements. That is what we have to find out. So first of all, find a D3 inside D such that D1 and D2 are less than or equal to D3. So this is because D is a directed set. Now since X is a cluster point of S, you will get a D4 inside D such that D4 less than or equal to D would imply SD is inside U1 intersection U2. I am choosing U1 intersection U2 as a neighborhood of X. For that I must have a D4. D4 less than or equal to D implies all such D's are inside, all such SD's are inside U1 intersection U2. That just means that D4 comma U1 intersection U2 is an element here, because SD4 itself is inside U1 intersection U2. Okay. So I can put D equal to D4 here, so that is there. Okay. First of all, this ordered pair is an element of E. It will be bigger than both D1 U1 and D2 U2. Why? Because D1 for example is less than equal to D4. D1 is less than equal to D3 and D3 is less than equal to D4. Okay. Right. So this is less than equal to D4 and UIs are all bigger than U1 intersection U2 because U1 and U2 are there and I have taken intersection. This proves that this is a direction only. Okay. So we have constructed a directed set. We have yet to construct a net that will be a subnet of S. Okay. For that, I take P from E to D to be the first projection. This is after all a product here. Take the first coordinate. So it is an element of D. So that is a function from E to D. Okay. P is from E to D, the first projection. Let us verify that P satisfies S2. Only then this P followed by S will be a, I can take it ST, that will be a subnet, right? So all that I have to do is P satisfies S2. Given a D inside D, choose any X comma, any D comma what, some neighborhood I have to choose. I have chosen X. D comma some neighborhood I have to choose. Okay. So choose the whole of x, then this will be inside x already. So that is an element of E. Then d comma x is less than or equal to d prime comma u. It just implies p of d prime is equal to d prime. That d must be less than or equal to d prime, because d is less than or equal to d prime is built in here. Okay, so that is the meaning of S2. So once you have that, I can take T equal to S composite P. So we have constructed a subnet of S. All that is fine, but we have to verify that this T converges to X. Okay, starting with a cluster point of S, we have got a subnet. I want to show that this converges to X, but that is not difficult. Once again, use the hypothesis that X is a cluster point of S. Given U inside an X, there is a D inside D such that D prime, first select D prime in D such that D is less than D prime, and SD prime is inside U. So that is because cluster point. Okay, we have such a thing. Now D prime comma U inside E, because SD prime is inside U. This is a member of E now. If D prime U is less than or equal to A U prime, take any member which follows D prime U, then U prime will be a subset of U. Okay, and T of A U prime by definition is S composite P of A U prime, which is nothing but S of PA. PA is A. It's SA. SA is inside U prime, because once A is bigger than this D, it will be inside U. Over. Therefore, T converges to X. So thus we have proved what? We have proved that criteria for a net to be having a cluster point, a subnet must converge. Okay, so that is the criteria. It is easy to see that in a discrete space, okay, we have this property, namely every sequence in it is convergent to every point, right? And you can characterize an indiscrete space by this property, namely if every sequence converges to every point, then it must be an indiscrete space. So this is an easy thing which you must have seen in the part 1. It's also easy to see that in a discrete space, on the contrary, see, I am taking these two extreme examples and what sequences can do to them. Okay, so if you take discrete space, every convergent sequence is eventually a constant, right? However, the converse is false, as seen in the earlier example. We have seen that one, right? Namely, the uncountable set with the co-countable topology. Okay, every convergent sequence in RCOC is eventually a constant, yet RCOC is not discrete, right? So what is the role of a net here? The net, on the other hand, has this property. A space X is discrete if and only if every net which converges to a point X must assume the value X. That's all. But don't say eventually constant and so on. Just assuming the value. If this happens for every net, that space must be discrete. So this is a powerful characterization of discrete spaces in terms of convergence of nets. Okay, a space X is discrete if and only if every net which converges to a point must have the value X. That's all. every sequence, that is every net it should be, not just one net. That is the whole idea. So let us prove this one. Suppose X is discrete and S is a net converging to some point X. Okay. Then there must exist D belonging to D such that D is less than equal to D prime implies SD prime is inside this neighborhood. Little x here, singleton x, is a neighborhood of x because every singleton is open. So I am choosing this neighborhood, and for that I must get this property because of convergence. D belongs to D such that anything bigger than D prime, SD prime must be inside it. Okay. In particular, S of D also, putting D prime equal to D here, S of D must be X. There is no other element here. Okay. So the value is assumed. Over. Now converse. Now suppose X is not discrete, then we will produce a sequence, produce a net which converges, and yet it does not assume that value at all. By the way, there are many sequences which are convergent which do not assume the value, which is the limit point, right? 1 by n, for example. So that is not a surprise. You should realize that. Okay, but this ordinary property characterizes the discrete space is something new, out of nets, not out of sequences. So you pay attention to that. So let us prove the converse here. Suppose X is not discrete, then there exists a point X such that singleton X is not open, because if singleton X is open for every X, then it is a discrete space. So not discrete means there is one point at least such that singleton X is not open. In other words, every neighborhood of X contains at least one other point. Therefore, we can construct a net now S from this neighborhood system Nx to X, which has the property that this S of u is inside u minus x. U minus x is non-empty just by our observation, namely our choice of x inside a non-discrete space, right? So this function again exists because of eczema choice. This S converges to X because given any neighborhood u of X, we can just take u itself, and for everything which follows that u, okay, u is less than or equal to v, implies S of v must be inside v, right? Because by choice here, but v is inside u, so S v will be inside u. Okay, so this sequence does converge to X. However, we have seen that it never assumes the value X because it's always inside u minus X for some u, for all the time. Okay, so one can go on doing quite a bit of net theory, but I would like to stop here and then take up the study of filters, and then as declared earlier, we will study a little bit of nets also in between. Namely, whenever the properties of filters comes close to the properties of nets also. Okay. In particular, there will be many more results on filters than just what you see for nets. Thank you.